So in the last video, you learned about indifference curves, which show us the different combinations of goods, of two goods that we could consume to get the same amount of utility or satisfaction. And you also learned about budget constraints and the budget line. Now, the equation for the budget line looks a little bit different than the equation that we learned in our graphing lectures, the slope-intercept form, but know that they're the same thing, and I'll explain how this is later in the video. First, let's take a closer look at budget constraint graphs. So, budget constraint graphs show us what combination of two goods we can consume for the same amount of money. So, for example, let's say that t-shirts are $7 each. And movies, they cost $10 each to go to see a movie. If we have a budget of $42 to spend on these two goods, how many of these two goods could we consume? So if we went to see no movies, we could we could buy 6 t-shirts, right? Because 42, which is our budget, divided by 7 is 6. So no movies, we get 6 t-shirts. Now, how many movies could we see if we got no t-shirts? For $42, we could see 4 movies, right? So they're $10 each. So those 2 points give us our line. We can connect them, and that's our budget line. And that's at $42. So what happens if we get a raise and we have a larger budget to spend? Let's say that our budget goes up to $65. Well, for $65, we could get 7 t-shirts, or we could go to see 6 movies. So here's our new budget line. So we've moved up. We've moved up with our raise. And that's $65 budget. So when you have a change in budget, budget, and this triangle here, this is a delta, and that's how we symbolize change. A change in budget, you get a change in demand, right? You have more money, you can buy more stuff if you look about decision making from that perspective. So that's our budget constraint graph and our budget line. So the equation of a budget line, we talked about it really briefly in that last video. The equation of the budget line is I, which this is really your budget. Income is what it stands for, but it's how much you have to spend on these two goods. So I equals the price of good Y times the quantity of good Y plus the price of good X times the quantity of good X. So this makes sense, right? If we multiply how many movies we see by how much they cost each, and we add that to how many t-shirts we buy times the cost of each t-shirt, we add those two things together, and that's going to equal how much we can spend in total. So if we compare that to the equation for a line that we learned in the graphing lecture, the one that looks like this is the slope-intercept form, remember? If we compare these two equations, they look really different, but they're not actually. We use different variables in our budget line equation because we're talking about specific things. We're talking about goods and their prices and the income, and we've swapped out those variables from the slope-intercept form. But they're the same thing. You could take our budget line equation and do some fancy algebra to it and move all of those variables around to be in slope-intercept form. But the issue with that is that when you move everything around to be in slope-intercept form, it looks really messy and it's hard to interpret. This is what it looks like if you do that algebra and you move everything around. It looks like quantity of y equals negative price of x over price of y times quantity of x over price of y plus the budget over the price of y. That's kind of difficult to interpret, but it does mean the same thing. So quantity of y is just your y variable. So that makes sense, right? Because we're talking about quantities on our graph. So y is the quantity of the y variable. The slope is this right here, this negative price of x over price of y. X variable ends up being quantity of x divided by price of y. And your y-intercept ends up being your budget divided by the price of y. And that makes sense too, right? Because if you take your total budget and you spend it all on, in this case, movies, if you take your total budget and you divide it by the price of movies, you're going to end up with the number of movies that you can see. So that checks out. So just know that this equation here is still the equation of a straight line, just like our slope-intercept form. It's just written in a different order. So let's talk about the slope of the budget line really quick, because this can get confusing for people too. We were told that the slope of a budget line is negative price of x over the price of y. So when we talked about graphing in the graphing lecture, we talked about slope. We said that slope was the change in y, the rise, over the change in x, the run, right? Remember that? So when we look at the slope of a budget line, you've got an x on the top and a y on the bottom, and what the heck, where did that negative sign come from? Well, it's okay. This is the same thing. This is the same thing as our slope. See, when we have this equation written in slope-intercept form, it ends up being negative price of x over negative y. And it makes sense that it's a negative, right? Because if you look at our line, it's trending down to the right. So as we consume more movies, we can consume fewer t-shirts. That's the indirect relationship that we talked about. Indirect relationship. It's trending down, so it has a negative sign. So we look at, for budget constraint graphs in particular, we look at the equation of the budget line and the slope of the budget line in these forms because it makes it easier to communicate the information. And remember that graphs and equations are all about communicating information. You want the viewer of the graph to be able to look at the graph and see what's going on and understand it. So even though they're the same thing as the slope-intercept form, this is how we look at them in economics. So let's look at the indifference curve again. So remember that indifference curves tell us the combination of goods that we can have for the same amount of utility. So if we have this indifference curve here, every point on this curve, every combination of, let's say, just goods y and goods x, that's a y, every combination that's on this curve is going to give us the same amount of utility. So we'll just call this 300 utils. That's how much utility this line represents. Now, we only talked about it as being one line, but really, there's an infinite number of curves here that could exist, right? Because each of these curves could represent a different amount of utility. So this one here might be 300 utils. This one might be 400 utils, 500, and so on. You could have any amount of utils, and you'd have a curve, a separate curve to describe that. So let's move over to a budget constraint graph. So we'll look at our movies versus t-shirts graph, and we have a budget line. So it looks like that. So what this is saying is that we could consume any combination of movies and t-shirts that sits on this line for the same amount of money. Therefore, any point that falls below that line, say down here, anything that falls below that line means that we are not spending our full budget. We're not getting as much stuff as we possibly could. Anything that's above this line is simply out of our budget range. We can't afford anything that's above the line. So if we combine the budget constraint graph, or our budget line, with an indifference curve, we end up with a really powerful tool. So let's see what that looks like. So on this graph down here, we're going to say, again, this is movies, and this is t-shirts. We have our budget line here. So we know that what we want to spend sits on this line. But the budget line doesn't tell us anything about how much utility we get from consuming any combination of these goods. And that's where the indifference curve comes in. So knowing that you could draw an indifference curve anywhere on this graph, you would want to find the indifference curve that runs tangent to, remember that word tangent from our graphing lecture? It just touches, it doesn't cross. You'd want to find the indifference curve that is tangent to the budget line, and the point where those two touch, that is the point where you get the maximum utility for your budget. Maximum utility for the amount of money that you can spend. I like to call it the bang for your buck point. This is where your budget meets your maximum utility. Okay, so this is an agricultural economics class. Why are we talking about movies and t-shirts? Well, let's move on to talking about something that's a little more relevant for agriculture. We can take this same idea, this combination of the budget line and the indifference curve, we take the same idea and we could apply it to all different kinds of things. We don't have to just be talking about money. Remember that economics is actually the study of how people make decisions, not necessarily about money. So how do people make decisions on how to spend scarce resources? Those resources, it could be money, but what are some other resources that we talked about? We talked about time as being a resource in one of our first lectures. We talked about water potentially being a resource. So let's look at those two things and talk through this idea again. So let's say that we are a farm that we have, so as the farmer, in one day we have 6 hours to spend on 2 different tasks that need to be done. We could spend that time planting. Maybe we have some squash transplants that need to go in the ground. We could also spend that time weeding, doing weed management on plants that are already in the ground. So how do we spend our 6 hours? 6 hours is the time that we have to spend in the day. Well, let's think about our consumption bundle first. Consumption bundle. Remember, that's the bundle of goods that you're talking about. And here we're talking about weeding. So time spent weeding or time spent planting. Those are the two goods. Oops. Those are the two goods that we are talking about. So if we took our 6 hours and we spent them all planting, we didn't do any weeding, that gives us this point right here, right? 6 hours planting, 0 hours weeding. If we did the opposite, spent all of our time weeding, none of our time planting, we end up right here. So this becomes our budget line. This is how we're budgeting our time. So next we would need to find our utility curve. And in order to find that, remember utils are not like a set definition. It depends on the person, and in farming it certainly depends on the circumstances. The weather is something that could change the utility. Say that it's going to rain really hard tomorrow and we won't be able to get out into the field and plant tomorrow, but that really needs to be done. That's going to give planting more utils than weeding probably. So you would have to find out how many utils you get per hour. And that's for the first hour, and then for the second hour, and for the third hour. Remember that it's not a constant rate. The utility often decreases the more, in this case, hours you spend on it. And you would need to find the same thing, the utils for your planting per hour. And with that information, you could come up with an indifference curve. And again, you would find where the indifference curve goes tangent to your budget line. And you would find, let's say that's the point where it's really tangent. So this point would tell you that the optimum way to spend your time budget, your 6 hours of work, would be to do 4 hours of weeding and 2 hours of planting. If your indifference curve lands right there. Now, like we said, what if it's going to rain tomorrow and you really need to get those plants in the ground and you won't be able to plant for another week if you don't do it tomorrow? Your utils for planting go way up. So your indifference curve might go way up here. And you might find that actually the best use of your time is to spend 1 hour weeding and 5 hours planting. So that's an example using time. What about an example using water? So many farms, let's say that we are a farm who irrigates using surface water. So water that comes from rivers or streams or lakes or irrigation canals, any of those things on the surface, versus a farm that uses groundwater, which come from a well. So we're using surface water, and we have an agreement with the other users of the surface water, or with the government. We have an agreement that we can use, let's just say 1,000 gallons per day. And in reality, this number would probably be a lot greater, but for our purposes, let's say it's 1,000 gallons per day. It's a nice easy number to think about. Now we could spend that 1,000 gallons of water irrigating, let's just say 2 crops that we have. We have an orchard, and we have dry beans. We're going beans for drying. That's our consumption bundle. Our consumption bundle is watering the orchard or watering our dry beans. Those are the 2 things we could spend our water budget on. Now, if we spent 0 gallons on our beans and 1,000 gallons on our orchard, let's say it gives us that dot. And if we do the opposite, spend all the water on the beans and no water on the orchard, we get there. So here's our budget line, our water budget line. So we would need to figure out our our indifference curve. So for that, we need to figure out our utils. And this might depend on different circumstances. Did you just water the orchard yesterday and it's been a week since you watered the dry beans? that would push your utils for dry beans up and your utils for orchard watering down. Is one crop a thirstier crop or have a greater water requirement than the other? Say the orchard needs more water than the dry beans. Your utils are going to go up for the orchard and they'll go down for the dry beans. So you would need to figure out, under all of these different circumstances, taking all these things into account, you would find out your utils for watering the orchard, for spending different amounts of water watering the orchard, and your utils for the gallons of water watering the dry beans. And again, you come up with an indifference curve, and you find the indifference curve that is tangent to your budget line, and that helps you find this point, this optimum point where the budget meets the maximum utility possible. And you find that you're going to spend this much of your water watering your beans and this much of your water watering your orchard. So again, economics simply about how we make decisions. Doesn't necessarily have to be about money, but if all other things in making a decision go away and we're just thinking about spending a resource or a budget for a particular resource, how much we can spend of time or money or water, whatever, spending a resource and utility or satisfaction, if we're just thinking about those two things, this is how the decision making happens.